All right, good afternoon. Let's start for chapter 11. Is that in tonight?
Yeah.
So make sure you complete that if you haven't completed it yet. The learning part for chapter 12 has been put on, so you can go through that. That's going to be due, I think I made it due next Monday, so even during finals week. What else? We have 3 more classes this week. Our final exam is next week, Thursday at 10:30 in this room. That's a 2-hour exam. Again, 50% roughly new material from the last 3 chapters and 50% from the previous material. I'm also going to be holding a review session. It's hard to find them during exams week, but if you do have time Monday evening, I think at 5:30 in this room, I scheduled this for a review session. So if you want some studying, we can do it then. Let's see, any other questions about the exams, the end of the semester?
There's no SI session tonight, is there?
SI session, I haven't heard that there's not, so I presume it's as scheduled. Mike's not here, is he? Okay, I want to finish up discussing some issues of aromaticity and arenes that we were talking about in chapter 11. So remember, when we think about aromatic molecules, there are certain requirements that we need that provide, when all of these things are in place, provide for very stable conjugated systems. And so we looked at the fact that the stability of something like benzene is related to, one, having full conjugation of the pi system. But that's not the only thing. It also has to be in a ring. And so if we compare 135 hexatriene with 135 cyclohexatriene, or benzene, we see that the energies of molecular orbitals and the way the electrons all align in there actually end up being in a lower energy state when it's in a ring. But that's not the only thing that's required for having aromatic stability. Although it helps to illustrate why, and we can see when we look at the electronic configuration of all the 6 pi electrons in benzene, they form these very stable systems where all the electrons are paired up in bonding orbitals. And then when we have rings with the different numbers of electrons, we have a problem. So even though fully planar and fully conjugated systems show aromaticity, not all of them do. They have to have the right number of electrons. Otherwise, we end up with situations where we don't have all the electrons paired up if it were to adopt that configuration. So here, for example, if you compare the electronic configurations of benzene, which is aromatic, 6 electrons and very stable, compare that to cyclobutadiene, which is fully conjugated, or would be fully conjugated and cyclic. But if we were to adopt this electron configuration the same way, we would end up with degenerate orbitals where there's electrons that are unpaired. Okay? So that only has 2 pi bonds, so there's only 4 electrons in the pi system. And we don't get to a stable situation if we were to do this way. So in reality, the actual electron configuration of butadiene doesn't adopt a symmetric one. It's actually like 2 double bonds that are not conjugated. And it adopts a more favorable situation, but not all the energies are in this orientation of it. Not all the orbitals are in this orientation of energy. If we have, so that's 2 electrons less than benzene. Here's 2 electrons more than benzene, 8 pi electrons. We see the same thing. In this cyclooctatetraene, we see that if we were to adopt this configuration of the orbitals, we would still have 2 electrons unpaired. And we saw that if we have even situations where we have charges, empty orbitals, or filled or lone pairs, in certain situations with a certain right number and size of rings, we could adopt a configuration which is stable. So it's not just neutral molecules which are aromatic. So Hubble's rule that requires 4n plus 2 electrons in the pi system in order to be aromatic, and n is just any integer. So if n is 0, that's 2. If n is 1, this equals to 6. That's benzene. Okay, 6 pi electrons. If n equals 2, the next stable aromatic molecule that's larger would have 10 electrons, 14, 18, etc. But not in between there. In between there, they're not stable. They don't get aromatic stability. All right, is everyone really clear about that? That's a really important aspect. Okay, well, when we were finishing last Friday, we were talking about other kinds of molecules that show aromatic stability, but they aren't necessarily all carbon in the ring. And I want to talk a little bit more about these. These are what we refer to as heterocycles. When we use the term heteroatom, we're referring to something besides carbon or hydrogen. But carbon, so these are heterocycles because they contain rings, but they're not all carbons in the rings. It could be nitrogen, oxygen, any other atom like sulfur, phosphorus. These are all referred to as heterocycles. You'll notice that various sized rings can have conjugated pi systems in them as well. So if we look at pyridine, this is pyridine. It's a 6-membered ring. What we would refer to as isoelectronic, meaning it has the same electronic system that benzene does. And the only difference is instead of 6 carbons like benzene has, we have 1 nitrogen. Okay? So I just want to compare that position. Notice in benzene we have 3 pi bonds, or 6 pi electrons. And in pyridine, we also have 3 pi bonds, or 6 pi electrons. So you do have that same aromatic stability. And the only difference is instead of having a hydrogen, like you would have, that's just all overwritten, isn't it? Instead of having a hydrogen on there, messing up my drawing. Okay, that's better. Benzene, with a carbon there, would have a hydrogen attached. Nitrogen being trivalent, there wouldn't be a hydrogen attached. And what we have is a lone pair. So just like the electrons in this CH bond of the benzene CH is pointing out away from the plane of the ring, the same is true in the pyridine lone pair, as you can see in this sort of side view of the electrons. The lone pair is orthogonal to the pi system. And you'll notice that the nitrogen already has a double bond to it. Okay, so you can't use, if there's a double bond or a pi bond already to the nitrogen, its lone pair can't be in the same plane. It can't be delocalized. It has to be pointing out up 90 degrees from the plane of the p system of the ring. So these double bonds, okay, 6 pi bonds in pyridine. Of course, we know this is just one resonance form, and we can draw them all as a circle because they're all delocalized. The lone pair is not. All right. Compare that to pyrrole. Pyrrole also has 6 electrons in the pi system, but in order to accommodate that, it has 1 fewer atom. It's a 5-membered ring. So there are 2 bonds between carbons and the lone pair. Okay, a total of 6 electrons. And in order for that to provide aromatic stability, those electrons have to be in a p orbital so that it can be delocalized throughout the 5-membered ring system. Okay. Notice in this resonance form, the stable resonance form that we draw for pyrrole, there's no pi bond written to the nitrogen. There's no double bond to the nitrogen. And that's a clue to know, to give you an indication of whether the electrons that are lone pairs are involved in the delocalization or not. If there's already a double bond, like in pyridine, those electrons can't be. If there is no double bond, those electrons could be in the same plane. Okay, and they have to be in order to provide 6 pi electrons to satisfy Huckel's rule. Okay. Similar to that is this molecule we call furan. Furan is the 5-membered heterocycle that's aromatic containing oxygen. It's similar to nitrogen, except, of course, oxygen is divalent. There's only 2 bonds to oxygen in its neutral state. And oxygen has 2 lone pairs. So to be aromatic, one of those lone pairs has to be involved in the pi system, and the other lone pair has to be orthogonal to that. So again, 6 pi electrons, but you only include one of those lone pairs in the pi system. All right? And another example, imidazole. Imidazole is this molecule on the right. It's a heterocycle which contains 2 nitrogens in the ring. Okay, and in this particular form I've drawn it, what you see is that one of the nitrogens has a double bond written to it over here, and one does not. So if you're to think about that, you should know which nitrogen lone pair is involved in the pi system and which isn't. Notice this molecule has 2 double bonds written in it, and so to have 6 electrons, we need 1 lone pair. So which nitrogen provides the lone pair for the pi system? The hydrogen with the nitrogen with the hydrogen attached to it. Yes, that's right. That's the lone pair right there, which is delocalized. There's no double bond already written to that nitrogen. The other one, this one has to be orthogonal, or 90 degrees. So in this picture I've drawn down here, this side view, this is the nitrogen whose lone pair is sticking out away from the plane of the ring. This is the nitrogen containing the hydrogen on it. Its lone pair is the one that's delocalized. Okay, so these kinds of aromatic heterocycles are really important. These just happen to be some structures for the DNA bases that make up the pairing within your DNA. And these or isomers, tautomers of these are aromatic heterocycles. And they are flat and planar. And they have lots of different atoms in it, nitrogens and oxygens. Nitrogens in the rings are involved in aromatic systems and stabilization because of that aromaticity. Well, if you think about this, we've looked at all of these different examples for heterocycles. Some of them have their lone pair available, and some have their lone pair tied up in the ring. Okay, so if you were to think about doing acid-base chemistry, which one would be a stronger base, which one would be a weaker base that is available to be protonated or react with a Lewis acid? Let's take a look at this on the next slide. Here I'm just showing pyridine and pyrrole, these 2 nitrogen heterocycles, one with a 6-membered ring and one with a 5-membered ring. Okay, both written has a lone pair, but if you really think about what's available throughout the pi system, pyridine, if you were to just draw the 6 electrons in a ring pi system, it would look like the structure on the right. And notice, to do that, I don't need that lone pair. That lone pair is orthogonal. Okay, so that means that lone pair is available for reactions. All right? Pyrrole, on the other hand, in order to be aromatic, this lone pair has to be delocalized. And I draw it with a ring. I have to include that lone pair in it. There is no lone pair available to react with an acid. Okay? If you were to react, by the way, it's not that you couldn't do it, it would just be really high energy. So if you were to think about taking pyrrole and reacting it with an acid, okay, take that lone pair, protonate it, Okay, what's the structure you make? It would be this, right? Nitrogen now has 4 bonds. What is the hybridization of the nitrogen? In this protonated form, what would be the hybridization of the nitrogen atom? sp3, that's right. sp3. So we know that in order to be aromatic, we have to have a fully conjugated planar pi system. That means every atom has to be sp2 hybridized. Only if that lone pair is available and delocalized can it be sp2. So by protonating perol, it's no longer aromatic because it's no longer conjugated. Okay? So why would it want to do that? You're going from a very stable state to a less stable state. So obviously perol is not going to be a very strong base. It's going to be hard to protonate. Pyridine, on the other hand, has this lone pair available. If you were to react pyridine with the acid, I'll draw it down here. Okay, pyridine, even if you, oh gosh, I'm drawing bonds all over the place. Let's get them right. Even if you protonate it, the pyridine still has a pi bond to it, a double bond. Okay? So you haven't interrupted the aromaticity of the ring by protonating pyridine. Pyridine is a pretty good base. I mean, not as good as hydroxide or something like that, but as a weak base, it's possible to protonate. You've noticed we've used pyridine before, right? In reactions that generate HBr or HCl, sometimes we use pyridine to neutralize that because that would react and protonate and neutralize and reduce that acidity of HCl. Perol you couldn't do that with. And if you have things like imidazole here, okay, it's going to only be protonated on one of the nitrogens, not 2. So if you were imidazole, which nitrogen would you allow to be protonated? Which one's protonated in imidazole?
The one without the hydrogen?
The one without the hydrogen. That's the lone pair which is available. Okay, so if you were to use this in an acid-base reaction, it has to be the nitrogen that has the lone pair available. Okay, if you protonated this one, it would be the same situation like we just talked about with perol. You would no longer have an aromatic ring. So it's important to recognize which lone pairs are available and which are not. By the way, this functional group, this heterocycle imidazole, is incorporated into one of the amino acids, histidine, and those have actually play the role in enzymes and proteins of doing proton transfers because it has lone pair available to take a proton and then give it back up. So it's very important for biology, this particular heterocycle. Okay, so aromaticity again requires planar, fully conjugated rings which have 4n plus 2 number of electrons in the pi bonds. Okay, and that can include double bonds and lone pairs, or any p orbital. Could be a carbocation or a plus charge that has a p orbital. sp2 atoms. All right. So any questions on aromaticity and how to recognize aromatic molecules? No? Okay, well, I want to talk about the reactions of benzene. And this goes on then to chapter 12. And the main reaction of benzene and benzene derivatives is this reaction we call electrophilic aromatic substitution. There's also a nucleophilic version of this, which we might not get time to talk about in this class. But the electrophilic reaction is a really important one for chemistry and synthesis. So if you think about the reaction that benzene does. This is an example of the electrophilic aromatic substitution. It's a substitution because we've substituted hydrogen for a bromine in this particular example. Okay, there was a hydrogen here that I've replaced with bromine, and we formed HBr as a byproduct. Nothing happens unless you have a very, very, very reactive electrophile. And so bromine itself, Br2, although it reacts well with double bonds that are isolated, like alkenes, we can do bromination of alkenes, it doesn't react with benzene. And again, because benzene is aromatic and stable. Okay? Only in the presence of a strong Lewis acid, like iron tribromide, what happens with iron tribromide? Remember, bromine has all these electrons around it. If I draw the Lewis dot structure for Br2, it'd look like that. Well, iron tribromide is a Lewis acid, and so it forms a bond with the Br2. What that does is make this bond weaker. It makes this very positive and this side very negative. Okay? Makes this much more electrophilic. Okay, more electrophilic. So if the pi bond that you want to react with is not reactive enough, you've got to make the electrophile that's adding to it even more reactive in order to get anything to happen. So this reaction, we're going to talk a lot about the mechanism of this reaction. Because although it's not just addition to an alkene, the first step still involves addition to an alkene. Okay, you just need a very reactive electrophile to do it. So I'm going to be a little generic and say, let me erase this, and talk about the mechanism. And this would be the reaction of any electrophile, which I'll just signify by E+. So I want to generalize this mechanism. E+ in that case would be Br+ for that reaction. But this works for any very reactive electrophile. So if we know something that's plus, and the electron density on benzene is in the pi system, okay, what happens when we add the electrophile to the pi system? Just like an alkene, I'm going to draw the hydrogen on this carbon for clarification. Every carbon in benzene has a hydrogen on it. Okay? If I add the electrophile to that by taking the electrons from that double bond, okay, I can draw an intermediate which looks like this. Right? That's the same kind of carbocation intermediate that we see when we add H+ to a double bond or any electrophile to a double bond. Okay? Now, in order to do this, I've broken the aromaticity, right? I now have an atom, the one with hydrogen, the one where the electrophile added to. I have a carbon which is now sp3 hybridized. So in order to get any reaction to take place, the activation energy is going to be quite high because you have to go and break that aromaticity, which takes away that stability. Okay? But that's what happens. Right? The difference is, instead of adding, in the case of Br, adding a Br- to that, we need to gain back that aromatic ring. It wants to go back to where it was. Okay? I can draw resonance forms for this. By the way, if that plus charge, if I take these electrons and move them there, right, we can draw the resonance structure, putting the plus charge here, and the double bond there, and I'm going to highlight this carbon that we added the electrophile to. Okay? There's a third resonance structure. So I could move these electrons down here, leaving the carbon on top empty. Okay, so there are three resonance forms. That plus charge is delocalized throughout the benzene ring in those positions, but we still have this in all of those. We still have this sp3 hybridized carbon. We need to gain back aromaticity. So how do we get back to sp2? Something has to come off. Okay, what comes off in that reaction of bromine?
Hydrogen.
Hydrogen. So we have a plus charge here. We have a CH bond which has electrons, and it can go to a very stable aromatic system. So of course, whatever is around, I'll just be generic, B minus. The counter ion for E plus. We'll grab that, and then those electrons will flow down to form the double bond. And so if that's Br2, you get a Br plus electrophile added to your benzene ring, and eventually the proton comes off to become HBr as the product. Okay, and we get back the aromatic ring. So we've substituted the hydrogen for bromine, but it's through a similar kind of mechanism that we think about electrophilic addition to double bonds. It's just once we add it, it's going to become more stable by removing a proton than by adding the second one. Okay, that's highlighted on the, do I have that on the next slide here? The mechanism, yes. So here's the mechanism for bromination, again, with the reaction energy diagram. So the aromatic ring reacts with a very electrophilic bromine, which is being activated now by binding to the Lewis acid. We add the bromine to that benzene ring. That carbocation intermediate, you can draw 3 resonance forms to delocalize it. But in the end, the hydrogen on the carbon that the electrophile added to has to come off to regenerate an sp2 carbon and satisfy that negative charge. And so we lose hydrogen bromide, and we gain back this. And notice what happens when we lose hydrogen bromide, that we get back our Lewis acid catalyst. So the iron tribromide really is just a catalyst in the reaction. We put it in, it activates the electrophile, but in the end, you gain back the same species. That's the definition of a catalyst. It's not, it doesn't change in the reaction, but it's involved in lowering the activation energy. And it does so by activating Br2. So notice the reaction energy profile. These are the possible pathways for this. Although it's a little bit exaggerated, that's probably not quite as high energy. But we have the rate determining step is a pretty high energy step to generate the carbocation intermediate by adding an electrophile. And then they can lose hydrogen and go back to the product that's now aromatic. Okay? The alternative, what we know from earlier alkene chemistry, if you add then to this a Br minus, right, to the carbocation, you would end up with this product. That product is no longer aromatic and would not be a favorable pathway for this reaction. Okay, rather it's faster to form this more stable aromatic species than the less stable addition product. Okay, so in terms of mechanism, it's the same that we've learned before in the first step. It's just that the second step diverges because it has a better path available to it. And this is general for all electrophilic aromatic substitutions. So substitute a hydrogen on a benzene for a bromine in this example. There are many things we can add that are good electrophiles. Nitration is a common one. Nitration is a reaction in which we've substituted a hydrogen on a benzene ring for an NO2 group. Okay. NO2, and by the way, I want to reiterate the Lewis structure for NO2. So if I draw that product, how do you draw NO2, Lewis structure? That's right, double bond to an O and single bond to an O. 2 atoms don't have the required number of bonds, so nitrogen has a formal plus charge and the oxygen has a formal minus charge. That's an NO2 group. By the way, I can draw the resonance form and put the negative charge on the other oxygen. I can draw it like this. It's like an acetate, really. That's the abbreviation. That's the resonance form. Now notice, in either of those nitro resonance forms, nitrogen always has 4 bonds and is always positive. Okay? Something to recognize. That will become important later when we talk about how that affects further additions. But for this, in this reaction, what we can do is introduce a nitro group into a benzene ring by electrophilic aromatic substitution, but we have to create a very reactive NO2 electrophile. This is NO2 plus. Okay? NO2 plus is very reactive. You can't just buy a bottle of NO2 plus and react it. So we have to make it in the reaction. Fortunately, if you simply take nitric acid and mix it with sulfuric acid, concentrated nitric, concentrated sulfuric, you generate, in that very strongly acidic conditions, a NO2 plus electrophile. It does so simply by, this is the structure for nitric acid, HNO3. And so what happens is you protonate it and lose water. Okay, let's say we protonate it here. And you lose water to form NO2. That's what's happening. So we have, when we mix these two strong acids together, we generate NO2 plus. NO2 plus will react with the benzene ring. Okay, so how does that react with the benzene ring? You don't know? What is the electrophilic atom in the nitro group, NO2 plus? N. N has the plus charge in NO2 plus. So if you were electrons from a benzene ring, you would attack that nitrogen and break one of the O bonds. So, I gotta draw over this, that's okay. So what you would form as an intermediate, I'll do it on the same carbon. Is the NO2 added to the benzene ring. It's just like E plus or Br plus that I showed on the previous slide. So you form the same kind of carbocation intermediate. You could draw 3 resonance structures for that. Okay, but to get to the product, what is lost is this will react with the H. Take the H off. We get the product and regenerate H2SO4. Okay? The proton comes off because we want to reform the aromatic ring. Again, the important thing is forming a very reactive electrophile in order to get any reaction with benzene initially. And so if we want NO2, sulfuric acid and nitric acid is the mix there, which is the nitric acid adding to it. Okay? What if we wanted to make, instead of NO2, we wanted to make a sulfonic acid? SO3H instead of NO2. How do you think we might generate some kind of reactive sulfur electrophile? Sulfonation is another reaction we can do. Sulfonation is shown on this slide. Notice benzene ring becomes SO3H in the product. And in order to form a reactive electrophile, what we need to do is start with SO3 under strongly acidic conditions. Sulfur trioxide is neutral because it also is zwitterionic. It has a plus and a minus formal charges. SO3, in the presence of concentrated sulfuric acid, simply gets protonated to form HSO3 plus. The sulfur has a formal plus charge. Okay. These are higher oxidation states of sulfur. It can handle that many bonds. So SO3, HSO3 plus is the electrophile. That's what gets reacted with the benzene ring, again, just like we did for the NO2. We form a carbon-sulfur bond. The structure for the product, I'll draw the Lewis structure again. We could draw this, it's drawn a couple of ways by people. SO3H might look like that, where the sulfur is neutral, or, let me just do this, or sometimes drawn like this. Either way is okay. But you can see that can be generated by attacking the sulfur with the benzene, the double bond of the benzene ring. You form the carbocation intermediate, which I'm not going to redraw again, and then deprotonate to form the aromatic ring. Exact same mechanism. All we've done is changed the electrophile, which is added. So SO3H2SO4 introduces a sulfonic acid group. Okay. Halogens, I showed you bromine already. We can do all kinds of halogenation reactions. It doesn't have to be just bromine. We can use chlorine, we can use iodine. Fluorine is a problem. F2 is a very, very reactive molecule, but it will just tear benzene apart, actually. It's so reactive. But bromine, chlorine, and iodine can be done. It's not quite so convenient to use FeI3, because iodine has the ability to become oxidized higher. But what your book, I think your book uses peracetic acid. Notice that's a CO3. Peracetic acid. Has 2 oxygens. Because of the reduction oxidations of iodine, we generate reactive I plus better by using oxidants. Or a Lewis acid like copper. I don't think your book used copper. Nevertheless, the reaction is the same for all of these. Either we're looking at a Br plus electrophile, a Cl plus electrophile, or an I plus as the electrophile, which adds. Okay, we end up with halogenation. I think one of the very important reactions, now these are all very good for introducing different heteroatoms, something besides carbon, onto the benzene ring, but ideally for organic synthesis, we want to be able to add carbon groups. Okay, so if you think about how to do that, what we need to add a carbon group as an electrophile is something that's really reactive electrophile. And what's the most reactive carbon electrophile you know? A carbocation, right? Or something that's really active. This reaction is more than 100 years old. Friedel and Krebs studied the substitution of benzene rings, and they found that when you take organic halides, like let's just say chloromethane, oops, did I go? What happened? Okay. That's better. Let's just think about chloromethane. When you take chloromethane and mix it with benzene, nothing happens. But if you react this with a very strong Lewis acid, like aluminum trichloride, and heat it up, it does take a significant amount of energy to do this. We get substitution of the hydrogen for the alkyl group. Okay, so what do you think the Lewis acid is doing? Yes?
It stabilizes the chlorine of the alkyl group and allows the carbocation to react.
Exactly. Aluminum trichloride is a Lewis acid. The Lewis base is chloride. And so what happens is that this reacts with aluminum trichloride. Okay. And I'll admit, 1 minute?
Yeah.
I'll admit methane itself does not form a carbocation. But chloromethane reacting with the aluminum trichloride. Again, it's withdrawing electron density to make that CH3 very reactive. So what do you think happens? This is the equivalent of a CH3+, but we know methyl carbocation is very high energy. What do you think happens? Benzene will react with the electrophile, which in this case is now CH3. And it does the exact same reaction. Electrophilic aromatic substitution, but instead of introducing nitro, a sulfonic acid, or a bromine, we're introducing a carbon. Okay, and so this actually forms a new carbon-carbon bond. This allows us to do an alkylation, and we get all kinds of opportunities then to use that for synthesizing larger organic molecules. Okay, I'm going to follow up more on this reaction next time. Right now, my colleague is going to come in and do the evaluations, class evaluations, so I would appreciate your help in filling those out. And we'll talk more about Friedel-Crafts alkylation on Wednesday.